Hello everyone, I'm Preethi Srikanth. Today I will be presenting Caveat Emptor towards transparency of IoT device presence. This paper explores the importance of transparency regarding the presence of IoT devices in our environments and proposes a solution to address privacy and security concerns. Let's dive in. This is the outline of this presentation. We're going to see the introduction of IoT and its challenges, what is the motivation of this paper, the proposed idea, and how the idea was designed and implemented. In addition to that, we're going to see the protocol and performance evaluation of it, and finally, we're going to see its limitations and conclusions. So let's we begin with what is IoT. It is a network of interconnected devices that communicate and exchange data over the internet, enabling automation and smart functionality in everyday objects. While IoT offers many conveniences, it also raises concerns. Unlike traditional technology, many IoT devices are embedded in environments in a way that they can go undetected. This lack of visibility creates challenges for privacy and security as these devices can often monitor, control, and even manipulate environments without clear user awareness. Today's talk will focus on this critical issue and a proposed solution to increase transparency in IoT enabled environments. So why does transparency in IoT matter? First, there is the privacy angle. Devices like cameras or sensors can gather sensitive data without the user's knowledge or concern. Beyond privacy, we have safety concerns also. So on that side, some devices called actuators can control elements in the environment like smart locks or alarm systems. Imagine an IoT device like a strobe alarm in a hotel room that could affect someone with epilepsy or a remote control lock in a rental property. These scenarios highlight the need for users to be informed of nearby devices and their potential impact. Thus, a primary objective is ensuring that IoT devices announce their presence and provide enough information for users to make informed decisions. This study has two main goals. The first is to introduce a system that makes IoT devices more transparent, ensuring that users in the vicinity are aware of these devices. The second is to create a model that prioritizes consumer awareness so users can feel confident and secure in IoT rich environments. Essentially, this study aims to make IoT spaces more transparent and safe. Achieve transparency, the paper introduces PISA, which stands for Privacy Agile IoT Sensing and Actuation, an architecture ensuring that IoT devices reliably announce their presence. This architecture includes both on-device components for regular announcements and user device components to receive these alerts. The framework is unique because it uses the ARM Trust Zone hardware-based trusted execution environment on each IoT device. With this setup, the device can securely make announcements even if its software is compromised. Through PISA, devices essentially say, I'm here and here is what I can do, enabling users to stay informed of nearby IoT activity. Next, we're going to see about the PISA design. In this, the core design objective is to establish a secure and reliable way for IoT devices to announce their presence and functionality. The design includes two main components, the IoT device, which is called here IDEV, which is responsible for periodically broadcasting its presence, and the user device or UDEV, which captures and processes these announcements to inform nearby users. In addition to this, we have one more component, that is MSVR, that is manufacturer server. It plays a critical role as the server responsible for setting up and maintaining secure connections. So, a key challenge in this design is ensuring that these announcements are both secure and tamper resistant, so users can trust that information received about nearby devices are accurate and free from interference. Then the PISA protocol has three main phases, that is registration, boot time, runtime. During the registration phase, each IoT device is provisioned with essential data like a unique ID and a keypad. In the boot time phase, every time IoT device is powered on, it synchronizes time with manufacturer server to ensure accurate timestamps for announcements. Finally, the runtime phase is the ongoing process where IoT device regularly broadcasts secure announcements, ensuring that nearby user devices can verify its integrity and status. So we will see these all phases in detail in upcoming slides. So when we see the Paizo's workflow, it begins with an announcement from IoT device. So this announcement is a broadcast message that contains essential information about the device's presence, type, and capabilities. Next, the user device. It captures this announcement and performs a verification process. So this step is crucial for validating that the message is authentic and trustworthy. Finally, after successful verification, user device notifies the user of the nearby device, giving them a clear understanding of its capabilities and activities. Then security is at the heart of Paisa's design, which is achieved through several mechanisms. First, each IoT device operates within a trusted execution environment, or we can call it as TEE. This secure area allows the announcement process to run isolated from other applications, reducing the risk of tampering. Additionally, PISA uses attestation to confirm the device real-time software state. So this ensures that announcements truly represent the current condition of the device. To validate the message, integrity and origin, each announcement is encrypted and digitally signed, allowing user device to verify that the message came from a legitimate source and has not been altered. Next, we will see the design challenges here. A primary challenge in PISA's design is mitigating denial of service, or we can call it as DOS attack, which can interfere with the device ability to broadcast announcements. So adversaries could overload device resources by forcing the microcontroller or network peripherals to run excessive tasks. To counter this, PISA designates both the timer and network peripheral as secure components controlled by the TE. This configuration guarantees that even under attack, the microcontroller shifts to the trusted computing base or TCB to issue announcements. This setup ensures that periodic announcements remain consistent and secure from interference. Bandwidth management is another critical challenge for PISA, especially given the potential for network congestion in IoT environments. So PISA addresses this by adopting a fixed size format for announcements. So each broadcast carries only the essentials like a URL linking to the device manifest, a timestamp to confirm currency, and a digital signature for authentication. So by minimizing data size, PISA ensures each broadcast remains efficient and non-intrusive on network resources. Moving to the PISA protocol, which is structured in three key phases: registration, boot time, and runtime phase, which we have seen in the previous slides. So these phases collectively enable IoT devices to securely announce their presence and status, ensuring transparency and security for users. So the first phase of the PISA protocol is registration phase, where the IoT device, or we can call it as IDEV, is set up with essential information by manufacturer's server. So I will explain how it works. So first, during the manufacturing process, each IoT device is assigned a unique identifier by the manufacturer server. It's also given a detailed description including device type, sensors or actuators it contains and its intended use. Additionally, the server generates a public private key pair specific to IoT device for authentication purposes. Then MSVR, that is manufacturer server, creates a device specific manifest which contains key information like the ID, the public key, a hash of the device software, and other metadata such as the device type, capabilities, and secure endpoints for retrieving updates. This manifest is then securely stored on manufacturer server and can be referenced by IoT device for broadcasting a summary of its capabilities and status. Finally, The manufacturer server securely installs software and specific configurations onto IoT device within its trusted execution environment. This ensures that PISA can perform secure announcements and attestations while protecting sensitive data and preventing tampering by adversaries. Once the registration phase is complete, IoT device enters the boot time phase every time it powers on. So this phase has three key actions: time sync protocol initiation, initial announcement generation, and timestamp protection against replay attacks. So the first action is time sync protocol initiation. To ensure secure and accurate announcements, IoT device initiates a time synchronization with manufacturer server through the time sync protocol. So accurate timestamps are crucial for establishing a legitimacy and currency of each broadcast, as they prevent replay attacks by providing an up-to-date record of the device state. After synchronizing its time, IoT device generates its initial announcement, which serves as a heartbeat or proof of life, signaling that it is operational and ready to begin normal broadcast. This first announcement includes its ID, description, and other relevant data that nearby user devices can detect and verify. So after that, the boot time phase enforces secure timestamping, where each broadcast has a fresh timestamp based on the synchronized time. This measure directly counters replay attacks, ensuring that only current information reaches the user device and that old announcements cannot be reused to mislead users. So with the setup complete, IoT device enters the runtime phase, which is its normal operational state. So the runtime phase consists of these essential steps, that is periodic announcements, software attestation for security, and verification by that is a user device. So the first is IoT device broadcast announcements at regular intervals defined by the manufacturer server. So each announcement includes a timestamp, a link to its manifest on manufacturer server, and an attestation result that verifies integrity. So this periodicity ensures that user devices receive timely updates about nearby IoT devices and their capabilities. Before each announcement, IoT device verifies its own software by checking the hash of its program memory against the secure hash stored in the manifest. This process, known as attestation, helps detect any unauthorized modifications or tampering of device software. So if the software passes attestation, IoT device includes an attestation report in the announcement. So finally, the verification by user device. So in this, when a user device receives an announcement, it performs multiple verification steps. First, it checks the timestamp to confirm the message is recent. Then it uses the manifest link to verify the device configuration and attestation result, ensuring the broadcast is authentic and the device software remains uncompromised. If all checks pass, user device displays the device presence and functionality to the user, providing transparency and security in the IoT environment. So these are the protocols, the phases. Then PISA has some security and performance requirements. So PISA's primary security objective is to ensure that each announcement is trustworthy and accurately represents IoT device current state. So for that, unforgeability is important. It is to ensure that only legitimate IoT device broadcasts are verified by user device. For example, if an adversary attempts to send a false broadcast, user device will detect that it lacks a valid signature, ensuring only authenticated information is accepted. Then timeliness. It is another key requirement. PISA is designed to prevent attackers from blocking or delaying announcements. Instead, they are sent at regular intervals, assuring users that they are receiving real-time information. Lastly, freshness guards against replay attacks, ensuring that announcements contain a timestamp that verifies their current relevance. Alongside stringent security requirements, PISA must be optimized for performance given the IoT ecosystem's limited resources. So low latency announcements are essential here. So PISA is designed to send announcements with minimal delay, ensuring the users is quickly informed of the IoT device presence. In parallel, low bandwidth consumption is prioritized to prevent network congestion, as even slight data overuse can disrupt IoT device performance and hinder the user's ability to receive updates. With these performance measures, PISA maintains a balance between robust security and smooth operation in real world scenarios. Next, we will discuss the implementation details of PISA, including the setup, components, and challenges faced in building this IoT transparency solution. So, the PISA setup includes the development board, network interface, and server and user devices. For the development board, the primary device used is the NXP LPC55S69 EVK development board, powered by an ARM Cortex M33 microcontroller with Trust Zone M support. This microcontroller allows us to utilize a secure environment for PISA's trusted execution. So for the connectivity, the ESP32C3 DevKit C02 board is attached to the main board, providing a 2.4 GHz Wi-Fi interface for sending and receiving PISA announcements. For the server and user devices, the trusted server, or we can call it as manufacturer server MSVR, is emulated on an Ubuntu 20.04 LTS desktop environment running a Python based server application. So for user device, a Google Pixel 6 smartphone captures and verifies PISA announcements via a custom Android app. Together, these components simulate PISA's operational environment, enabling secure announcements and transparent device presence. Then, ensuring secure operation in PISA, it involves configuring trusted execution and handling faults. So for the secure peripheral setup, PISA configures the CTI MER2 and UART4 peripherals as secure components using Trust Zone M. This setup ensures that only the PISA trusted computing base can access and control these peripherals, blocking unauthorized access. For the fault handling, if an adversary attempts to interfere with these secure components, a secure fault will be triggered. This fault handler immediately resets the MCU, preventing the attacker from disrupting PISA's announcement processes. For the announcement priority, to maintain timely announcements, PISA's secure timer interrupt has the highest priority. This priority setting ensures announcements proceed on schedule, uninterrupted by other tasks or user level interrupts. These security features uphold the reliability and integrity of announcements, ensuring the device remains transparent and protected from tampering. Next, the IoT device contains three main applications: a non-secure thermal sensor application, a PISA trusted computing base, and a network stack with a secure UART interface. The non-secure application reads temperature data from a sensor and sends it to an external server even though the network interface is secure. To allow access, IoT device uses a secure stub that gives non-secure applications network access while still prioritizing PISA announcements. For security, cryptographic operations are handled using the Ember TLS library, where IoT device and its counterpart manufacturer server exchange ECC public keys created on the Prime 256 version 1 curve. Now, the PISA TCB itself has three modules: a secure timer, attestation, and announcement. The timer is triggered by an interval called T-announce, and it first runs the attestation module, which verifies the software's integrity by computing a SHA 256 hash. It then calls the announcement module, which sends a message to the network interface using USART. Finally, the network stack uses an ESP32 board operating in station mode for syncing with manufacturer server and soft AP mode to broadcast announcements. Once a message is received, it's transmitted as a beacon frame with the SSID PISA containing message details for secure communications. On the user side, the PISA reception app runs on an Android platform, providing users with a transparent view of nearby IoT devices. So for the platform, it is built for Android. The app was tested on Google Pixel 6 and leverages Android Studio for development, providing a familiar interface and integration with device capabilities. And using the get scan result function API, the app scans for Wi-Fi beacon frames with the SSID PISA. This method enables the app to identify nearby PISA devices even without direct pairing or network connections. For the verification and display part, upon detecting a beacon frame, the app verifies a message anno using the cryptographic keys associated with each device. If valid, the app retrieves the device manifest, displaying details such as the device type, manufacturer, and attestation status, etc. This reception app offers users a clear, secure way to access information about nearby IoT devices, promoting transparency and trust in IoT interactions. So, PISA's implementation faced specific challenges unique to IoT environments. So, first is announcement broadcasting. Since direct connection between user device and IoT device is not always possible, PISA leverages Wi-Fi beacon frames to broadcast announcements. These frames are typically used by routers, but PISA uses them to convey secure announcements, ensuring that nearby devices can receive a message. Second one is message size limits. So the message is compressed to fit within the 255 byte limit imposed by the Wi-Fi standard. By utilizing efficient encoding and reducing unnecessary fields, PISA condenses essential data like the manifest URL, timestamp, and digital signature into a compact form. The last one is signature processing overhead. The cryptographic signature process adds overhead to the device processing, but PISA optimizes this by using efficient algorithms, reducing latency while maintaining security. So these solutions enable PISA to broadcast secure announcements despite bandwidth constraints and processing limitations, balancing transparency with performance. Then we will explore the performance evaluation of PISA, focusing on 50 iterations to provide a reliable measurement. The evaluation centers on three devices, that is IoT device, user device, and the manufacturer server, each responsible for a specific task we already know. But the paper analysis is divided into two main phases, boot time and runtime. Boot time represents the initialization phase where essential configurations and synchronizations occur. Runtime, meanwhile, captures ongoing operation and overheads, particularly focusing on the PISA announcement module. So, for the boot time, for the IoT device includes three key steps: init device, time sync, and announcement. During init device, the device initiates essential peripherals such as the microcontroller, sensors, actuators, and network interfaces, completing this in about 9.66 milliseconds with negligible variance. Following this, time sync is executed where the device connects to manufacturer server over Wi-Fi in station mode using UDP. This phase also involves clock synchronization between IoT device and manufacturer server with a mean latency of 1080 milliseconds and a standard deviation of 187 milliseconds. The significant delay is due to network latency and the cryptographic operations required, two ECDSA signing operations and one verification. Each of these operations at 150 MHz takes about 230 milliseconds. Finally, the announcement step sends the device first message anno taking around 236 milliseconds. This step includes one signing operation and transmission of a beacon frame. In total, boot time is approximately 1300 milliseconds, primarily due to time sync and announcement. Since boot time happens infrequently, this latency is considered reasonable. Once boot time is complete, the device transitions into runtime where the PISA announcement module operates. Runtime performance mainly focuses on the latency of message generation and signing. So each announcement includes a fixed size signature, resulting in a constant latency of around 230 milliseconds for signature generation. In contrast, attestation time varies with the size of the memory being attested, scaling linearly, taking only about 1 millisecond for each 64 KB. Even with larger memory sizes, like up to 1 MB, the attestation process remains efficient, completing in about 16 milliseconds, which is 14 times faster than a single signing operation. Furthermore, the network overhead during announcements is negligible at just 135 microseconds, ensuring minimal impact on overall latency. Moving to user device, a Google Pixel 6 in this evaluation, they access the latency of message anno reception. Receiving a single message takes an average of 1070 milliseconds with a standard deviation of 247 milliseconds. The high variation stems from two main factors like network delays and context switching within user device, which has heterogeneous cores with frequencies between 1.8 and 2.8 GHz. Despite the relatively high latency for a single message, user device can process multiple messages concurrently using asynchronous task, meaning the reception latency has minimal impact in cases where multiple devices are active. Finally, let's look at the performance of the manufacturer server during the time sync phase. The server handles one signing operation and two verification operations for each connected IoT device. These cryptographic tasks are efficient, taking only about 1 millisecond each on a 2.6 GHz server processor. The average latency for time sync at the server is just 5.6 milliseconds with a standard deviation of 2.77 milliseconds, primarily due to network delay. Given manufacturer server's capability to manage multiple devices in parallel, this latency remains reasonable even under load. The next is manifest IoT device and TCB sizes. The manifest IDEF size depends on several factors, including the cryptographic algorithm, key size, certificate types, and encoding methods. For this evaluation, the size used was approximately 2857 bytes. Additionally, the trusted computing base size for PISA is essential to ensure a secure environment. On the main NXP board, the TCB size including embed TLS is about 184 KB, while the TCB on the network ESP32 board, which includes the network stack, is around 682 KB. These sizes reflect PISA's minimal footprint, making it adaptable for low power IoT devices. PISA has several limitations, each with possible solutions. First, runtime overhead. It can be managed by adjusting the announcement interval, balancing CPU use for applications versus announcement responsiveness. Next, TCB size. It increases attack surface, but pruning unnecessary network protocols reduces this. Compatibility is broad, supporting various roots of trust and network interfaces like BLE and cellular, though adjustments may be needed. For secure updates, authorized tokens can enable safe firmware updates on IoT devices. User linkage can be addressed through privacy preserving techniques like Tor or cryptographic methods. Uh, then, to counter DOS attacks, PISA requires a dedicated network interface, or alternatively, a shared secure step can handle both secure and non secure functions. Lastly, server overload at manufacturer server. It can be alleviated by certified third party servers to handle requests. These strategies enhance PISA's efficiency and security for IoT applications. Then, in the development of PISA, several areas of related work have been explored and classified into six categories. First, active roots of trust. These are systems that actively secure MCU operations, preventing software compromise. Then, remote attestation is another area, focusing on verifying device integrity remotely, which is essential for PISA security goals. Next, ARM trust zone technology. It is highlighted for isolating sensitive tasks, making it applicable for securing IoT environments. For hidden IoT device detection, traditional methods rely on special hardware or Wi-Fi traffic analysis, but they are either too complex or error prone. PISA improves this by simplifying nearby device detection. Broadcasting beacon frames has also been studied, showing how Wi-Fi frames can communicate device info without needing network association, similar to PISA's announcements. Lastly, in IoT privacy, past research has introduced privacy assistance, consent mechanisms, and security labels. These findings guide PISA to include user-friendly privacy features in its manifest IDEV. Together, these prior works underscore PISA's innovative, systematic approach to IoT security and transparency. Overall, PISA shows how IoT devices can be made more transparent to users without compromising security, opening doors to more privacy-respecting smart environments. So then these are the references that I have been used for the presentation, and thank you for watching.